Hi, and welcome to this project video, part 1 of the tapping block project. Now, what is a tapping block? Well, it's a block that has accurate holes drilled into it and that has accurate surfaces. And this block, once you insert a tap into it, helps to align the tap to the surface that the block is resting on. So it's really just a tool to help start taps nice and perpendicular to their surface, or if you prefer, parallel to their hole. So that's what we're going to be making. Now this is a quite small tapping block because it's for small taps. Now I'm going to be making several of these blocks for a couple of reasons. And the first, it might seem a little bizarre. The first is I'm going to be making 3 or 4 of them that I'm going to send away to get finished by surface grinding by another or a fellow YouTuber, YouTube machinist. A guy called Brad Jacob, a basement shop guy, maybe you know him by his YouTube name, and he has a nice site. Okay, so Brad Jacob decided that it would be nice, and I fully agree, to get a bunch of YouTuber machinists together to produce cooperatively some tools that could be sent off to a great YouTuber, Keith Fenner, who each year organizes and does an incredible job of organizing a tool giveaway that's called What's in Your Box. And I'm very happy to be able to participate in a very small way. So some of these blocks, 3 or 4, I'm going to produce oversized. I'm going to leave some material on for grinding, and they'll be sent off to be ground by someone else, and eventually they'll make their way to Keith Fenner. But I don't want to leave the home machinist hanging, and we know that home machinists, and not a lot of them, and I certainly don't, have surface grinders. Because we just don't use them that often. So fine, so we don't have the surface grinder. Does that mean we can't do the project? No. That means that we're going to finish some blocks to a smaller dimension, closer to their final dimension, and we can finish them by lapping or by abrasive machining. So we'll see what we can do there, and we'll end up with 3 or 4 tapping blocks finished in a way that most people could finish them in their home shops. So we'll see the best of both worlds, surface grinding and different ways of hand finishing a hardened workpiece. So this is a great little project, I find, for learning, because it encompasses a lot of basic techniques. And for those young teachers out there, teachers in machine shop that are looking for good projects as a first project that a student could work on, even at a middle school or a high school level, well, this is a great project for a beginner, someone who's just starting out. So let's get to this tapping block project. Before we start cutting, it's important to note here that since I'm holding this part just on the edge of the vise, and that makes quite a lever here, I'm supporting the back end of this smaller movable jaw with a screw jack, and that gives me extra leverage that I can really tighten down to ensure that my part is properly held. And here's what I end up with. A rectangle, a cubic rectangle I guess we could call it, that is going to become several smaller parts. I'm thinking of getting about 3 to 4 parts from this part here, smaller cubes. And actually I have 2, so I'm looking at 6 to 8 different pieces. We'll see how many we can get out of there. But The problem being that I don't want to have to square up that many blocks independently. So to save a little time, I'm going to square up this whole cube before I cut it into lengths, and that will actually save me a lot of time. So let's head over to the workbench to set this up in a vise, to deburr it, and to prep the part for milling. Now all I want here to start the milling process is one good flat surface. Doesn't have to be perfectly flat, but a reasonably flat surface that I can hold into the vise. If I end up with two opposing surfaces that are nice and flat, well then that just makes my life a lot simpler. So we'll see what we can do with these. Let's head over to the workbench and prep these for milling. First operation, well, is going to be deburring. Now, there are massive burrs on the surfaces that were just cut in the saw. And the other surfaces have almost no burrs. Actually, I suspect I had deburred them previously, but we'll run a file over them anyways. When you have large burrs, take the time to stabilize your part in your bench vise. It's there for a reason. Now, you're going to be taking good cuts because we have large burrs. A stabilized part means control. Control means safety, because that permits you to use both hands on your file and work in a controlled fashion. The other surfaces, or the other intersection of surfaces, or edges I should say, as I mentioned, are pretty well already deburred, but just to make sure there's no snags or hooks or sharp ends, I'm just going to handheld lightly file. I can do it handheld here because I'm really not applying much force. It's just to make sure that all is well, and I can feel that this part is not sharp in any way and is properly deburred. So, next operation, descaling. Since this part is hot rolled, that means that it was finished very hot at the mill, and that means that it's quite scaly. Now, the scale on hot rolled steel is actually carbide, and it's very, very hard. But it's not too difficult to get off, but it can wreak havoc on cutting tools. So, if possible, it's best to remove it before machining. And for that, really, you can sandblast if you have the equipment, or keep an old grinding wheel at hand, something that's reasonably coarse that you can use to get rid of that scale. If the crust is particularly thick, you can sometimes remove most of it with the hard face of a hammer. This little positioning hammer, its steel face is quite hard. I'm just going to lightly tap the surface to chip away most of the thickness of this crust. This is very dangerous for your eyes. Wear your safety glasses at all times. Now, once the part has been descaled, you want to choose the best surface. The best surface in this case is the flattest surface, as long as it's not one of the small end surfaces. Any of the other four surfaces will do here. So choose the one that seems the flattest, okay? And I'm calling this one as being the flattest, and we're going to lap that one surface. It doesn't have to look pretty, it just has to be flat. And for lapping, well, we can use a lapping plate. and we spoke about lapping plates in our lesson on bench work, so the bench work lesson video. I don't know which part of that video it was in, but we spoke about it. With its grooves, the plate has grooves to accumulate abrasive paste in it, and then we can lap our part. But not very many people have these, and I wouldn't buy it just for that. That was one I made, so I didn't buy it at all. The other option that you have is to use a flat surface, a surface plate or some kind of very flat surface, and abrasive paper and a bit of oil. And you can lap on the flat surface with your paper, oil stuck right onto the surface and oiled to promote proper cutting action. And that is also a way to do it that's accessible to most people. I mean, we all have a flat surface somewhere that we can use if we're working in a machine shop. Or you can use one of these inexpensive belt sanders, okay? Now, we're not using it to square up our block. And as I say, I'm not going to be removing a lot of material. I just want to make myself a flat surface. And since I'm lazy and that this requires very little effort, well, this is the method I'm going to use. We're just going to barely touch it up so that I get one flat surface. So there's my surface. A quick rocking test to make sure that it's nice and flat, followed by a comparative flatness test with a piece of shim stock. And I can say that I have a nice flat surface. Well, nice, not pretty, but I have a flat surface that I can use as a reference for starting to square up this block. So now we're ready to head over to the mill, but before we do that, I'm going to go wash my hands because I made a real mess of myself here taking that scale off. But even more important than that, there's a question that many of you want to ask me by now, and that is, why did I cut the block in two when I could have squared up the whole block and saved even more time? Well, you are right if you'd figured that out already. I could have saved more time by not cutting the block in two right off the bat. But what hasn't been said is that this is going to be two projects. Now, as mentioned at the start, this is a project that's for the What's in Your Box toolbox giveaway that Keith Fenner does every year I should say. And I'm participating with many other YouTubers to make this, and some of these parts are going to be sent on to someone for surface grinding and finishing, and those blocks will be left slightly oversized. But I don't want to leave you hanging because many people don't have surface grinders, so I'm going to be doing the project twice. Actually, more than that. I'm going to be showing many ways of finishing a project like this. And one of these blocks is going to be cut almost size per size. So one is going to be about 0.10 of an inch oversize per side, and the other is going to be pretty well size per size. And now we can head over to the mill. So there, my vise is aligned within 1/1000 of an inch, and it's really almost bang on 1/1000 of an inch out. I'm not going to make myself sick here. This project isn't that accurate, and you have to remember that size does matter. Now I have a 4-inch long fixed jaw on my vise aligned to about 1/1000 of an inch. The part that I'm producing in that axis is going to be about a 1/2 inch, because my final part here is going to measure 13/16 by 5/8 by a 1/2 inch, and the 1/2 inch is going to be in that X dimension. So if I'm about at 1/1000 over 4 inches on a 1/2 inch in that same axis, I'm going to be very, very accurate. So 1/1000 in this case is more than good enough. So next step is going to be installing my cutter, and I'm going to be using this 2-flute carbide insert face mill. Okay, it's not really made to cut on its side, it's a face mill. It's a 2-flute and it has these triangular inserts. Really inexpensive, and what's nice about the triangular type with the zero rake on them, so it has a neutral cutting angle, is that they can be indexed 3 times. Obviously they have 3 points, so if one point gets worn down you can turn to the next and keep going. So 3 cutters out of each insert. That's a good deal, and they're really not that expensive. So this is the one I'm going to use. I'm cutting a piece of 4140 medium carbon alloy steel, and its cutting speed is 70 RPM. So that means that for a carbide, I'm going to be cutting about 4 times the speed that I would have calculated for a high-speed steel cutter, and that will give me somewhere between 800 and 900 RPM. Now the closest that I have on this mill is 770 RPM. That's the closest speed that doesn't go over what I calculate. And that's important because what we calculate is a maximum. So 770 RPM is what I'm set up at, and that's what I'm going to cut at, and that's fine. Now, for the vise alignment, if you're not sure what's going on there with the dial indicator, well, I have a video for that, and you can go see that on my website. THATLAZYMACHINIST.com has all my videos, and I think the project and alignment shop videos, things like that, are on the 3rd page in English. And if you don't know what I'm talking about the speed calculations here, well, on that website, in the shop videos, the 3rd page in English, you're going to find a video on chips, speeds, and feeds that will explain how to calculate all those things, so you can go take a look at that. For now, we're going to install this 2-flute face carbide insert mill into the spindle of this machine using an R8 collet. Okay, so my RPM is set, my vise is aligned, my tool is installed, and I've rough set the height of the head so that I'll be milling approximately where I'm going to be milling, so that the quill is as retracted as possible. Now I'm going to have to move a little bit, but just a very little bit. Now remember, the more the quill is extended during a milling operation, well, the less rigidity I get from the machine, and that's really going to affect my cutting performance. So everything's set up except for the part, so let's install the part in the vise.
So I'm going to set up a parallel, make sure everything is really nice and clean. We don't want any chips interfering here. So one parallel to support my part. There's the prepared surface, and there's the surface I want to cut. So I'm going to install the prepared surface up against the fixed jaw, and another parallel, but not under the part. This one's going to be used to just hold this cylinder at the proper height. Now that cylinder is going to redistribute the force that my movable jaw is applying.
There, my part is tightened down, good and tight. Now, there's a few things going on here, and in the squaring up a block video from my webpage, you'll get a lot more explanations about it. But just quickly here, I have one parallel under my part, and as we've seen, I put my prepared flat surface up against my fixed jaw because that's my reference. That's what's going to start everything off square. Now I put a parallel under the part just to roughly align it parallel to the top of the table. That surface underneath there is hot rolled. I cleaned it up, but it's really not a pretty and nice and flat surface. But I still want to get the part as parallel to the table as possible, just because I don't want to waste material. If the part was really crooked in the vise, well, one end would be a lot thinner than the other, and oftentimes if we don't pay attention to aligning it roughly in that plane, well, we end up with a part that's undersized on one end. So it's about parallel, and that's what my one parallel there is used for. But you notice that I didn't hit the part to sit it down. I just wanted that parallel to bring it about horizontal or parallel to the table. I don't have to sit it down onto it with a mallet because that surface under there isn't good. So what good would that do? I'm just going to let it sit naturally up against that fixed jaw. And that, as I said, will start everything off nice and square. I also used a second parallel, not under the part here, but just to support a small brass cylinder that is going to push or apply the movable jaw's pressure evenly over the part. Now, it's very important here that this part be well seated against the fixed jaw. If I just tighten the jaw against the other end, and the other end or the other side of the part here is askew, well, I might be holding only on one corner. And that's what this little brass cylinder is for. Why brass? I could have used mild steel here, something soft, but not lead. It doesn't have to be, it shouldn't be very, very soft. But I want something that has some bite to it, that when I tighten down, it's going to mush a little bit into the part and a little bit into the jaw to stabilize everything. So I am ready for my first cut. So let's line our cutter up to the part and take that cut. Take a look at this. My y-axis, this axis here, is set up. And I can see that I'm just past this edge of the part, but I'm quite a bit past this edge of the part. In other words, I didn't center the cutter on the part, and I did that on purpose. Now, why is that important? Well, it's the whole Klein milling, conventional milling thing. Now, this isn't exactly the theoretical Klein and conventional milling, but it's the same principle. I have a tool that's rotating clockwise, and if the tool were centered on the part in the direction that I was feeding, as I fed the part towards myself here and under the tool, well, the tool would be pushing the part more or less directly onto the fixed jaw of the vise. And that's good. I want the force to be directed towards the fixed jaw. It's the most rigid and the most accurate of the jaws on the vise, so that's fine. But I do have backlash in my lead screw, and that is a problem because that introduces vibration and even the possibility of snagging and grabbing a part. So to avoid that, I offset the center. Now, had I gone the other way, clockwise rotation, and had I been more on this side of the part, well, I would have been pushing towards the fixed jaw and pulling the part towards me, what we would normally call climb milling. And that's a problem because the backlash is, if I'm feeding towards myself, the backlash is in my direction. And if I pull on the part in my direction, well, I can jump ahead. In other words, eliminate the backlash quickly by pulling on the part. And that breaks cutters, and that is not a good thing. It's dangerous. I want to eliminate the backlash, and to do that, I want to push the part against the fixed jaw, yes, but I want to push the part away from myself at the same time. And by installing the cutter in the way that I did, the cutter starts its cut by pushing mostly forward, and as it progresses through the part, it pulls the part towards the fixed jaw. So that means that cut after cut, I'm pulling towards the fixed jaw, which is good. I'm pushing the part towards the fixed jaw, but I'm also slightly pushing it away from myself in the opposite direction of the backlash. And that's what we'd call conventional milling, and that is a lot safer. You can't snag a part when you're pushing it away from yourself as you're feeding the part towards yourself. There is no backlash. So it's important to not always center the part. I know most people center the cutter on the part just naturally, but really it's not the way to go. Now, other thing, an axis that is not in use is a locked axis. There is no ifs, ands, or buts about that. If you're not using it in an operation, it is locked. And if you are using it in an operation, it's not a bad idea to snug it up a little bit at least. You want to reduce vibration, you want to reduce the possibility of movement here. So my y-axis is set here, and that means that my y-axis is now locked into place. I'm not using it after this cut. All the other cuts are going to be about at the same place, so my y-axis is locked in position. I don't have to worry about it moving or vibrating. Now, let's take that cut. Now, if you thought this was going to be action-packed, well, I guess you're out of luck, because there's another thing that I want to mention here, and this is a teaching video, so safety is important. And right now we can see that this cutter isn't in interference with the part, but it is close to the surface and it is clearly above the part. That is not a good position for turning on the machine. We get used to turning on machines when tools are that close to the part. Well, eventually we're going to get ourselves into trouble, because one day we're going to turn on the machine and we're going to have interference, and that can really wreak havoc. So a good practice is to back the tool off, generally in the axis you're cutting, just to ensure that you clear the part before turning on the machine. It's all a question of habits. Now, these 2-flute cutters aren't bad. The 4-flute cutters are even better because it's easy to see interference. But if you get used to starting with possible interference because you look visually and you're satisfied with what you see, well, that's all fine and dandy, but someday you're going to get a fly cutter on your mill with a single lip cutter, and those can really fool you. So if you get into a bad habit now, well, you're going to carry that bad habit throughout your work and eventually get yourself into trouble. So I'm not going to turn it on here, I'm going to back it off first. So what I'm going to do here is I'm going to back off just to permit myself a clear space to turn on the rotation. I'm going to approach the part with the tool in rotation. Once I'm above the part, I'm going to adjust my z-axis, my depth of cut. And here I'm really just setting up my first surface to be cut. So the depth of cut here isn't important. What is important is to not burn bridges. So I want to take the least amount of material off here to just flatten that surface and keep all the material that I can keep for other surfaces to get me out of trouble if I need it. So that's what I'm going to do. So let's take that cut. So there, our first surface is cut. I'm going to do the same thing on my second block because we have two parts to square up here. And then I'm going to deburr them before moving on to the other surfaces. But that's enough for the part one of this video. In our next video, we're going to be finishing the squaring up of the two blocks, and then we're going to be doing some side milling to establish our tertiary references, and we're going to be cutting up our blocks and finishing them to their pre-heat treatment dimensions. So, until then, have fun, be safe, and happy machining.